electrical conductivity, heat-resistant properties, and were easy to work with in a fibrous form. This added commercial value and in a point of time improved safety in specific instances of use. However, over time, exposure to asbestos was found to be more harm than benefit through the epidemiological association to the outcome of disease. Consequently, this has imposed regulatory requirements in the prohibition of its use and the development of standard methods of analysis in support of regulatory requirements and predicting the outcome of disease. The main focus that I'll have here today is on the workplace health and safety regulations and the associated analytical methods. So the New South Wales Workplace Health and Safety Regulations defines asbestos as the following 6 mineralogical varieties of actinolite, amosite, anthopolite, chrysotile, chrysotolite, tremolite, or a mixture of the above. This then leads us to consider further definitions of what a mineral is, how it may be classified as serpentine or amphibole, and finally the term asbestiform. A mineral is a naturally occurring solid substance formed by natural geological processes with well-defined crystalline structure and chemical composition. For the mineral silicate to be asbestos, the morphology of the material must be asbestiform, this being a special type of fibrosity. So who is it then that can analyse the material and determine whether it fits within the definition of asbestos? So Regulation 423 stipulates that the analysis of a sample must be conducted by a laboratory operated by the regulator, a lab approved by the regulator in accordance with guidelines published by Safe Work Australia, or a NADA accredited laboratory accredited for the relevant test method. In the majority of circumstances, a sample will be analysed by a NADA accredited lab. So in a sense, it's NADA who defines what asbestos is by the regulatory requirements and the methods that they approve in analysing a sample. So this has been fairly simple, as all accredited laboratories have historically been accredited to the Australian standard AS 4964. But there's been a change in the landscape recently, where over the past 2 years, labs have been accredited to international standards, in-house methods, and guidance documents from other regulators, such as the UK Health and Safety Executives Analyst Guide. And this is where traditional optical microscopy has been used, with there being recent approvals of alternative techniques of electron microscopy and X-ray diffraction. This now introduces some variation in the definition of asbestos, depending on the method in which the material is classified. The differences in methods or standards may nominally at first appear to be negligible. However, they can be significant. And this is quite pertinent given that NATA has now removed the long-standing requirement for unequivocal identification of asbestos. So to classify a material as asbestos, we need to characterise its identity. Identity may be concluded by comparing property values or a combination of property values that are unique to that material, and it essentially becomes a specification. The measurement results and observations via the analytical methods provide evidence in support of the material conforming to those specifications. Where there's concordance with the specifications, this supports the material's identity being classified as asbestos. And when the specification isn't met, then the material is not classified as asbestos. There may also be situations where the classification is indeterminate. The use of different observations and results which are compared with a well-established and predefined criteria is also known as a panel test arrangement, being a somewhat more formal weighted evidence approach. This is where even one technique can be considered a panel test in itself, such as polarized light microscopy, where this provides a number of observations in different lighting conditions. And unequivocal identification can be made for the majority of commercial products containing chrysotile, amosite, or crucidolite. This then leads to the question as to what property values must be specified to unequivocally establish the candidate material's identity as asbestos, and what analytical techniques may be used to compare it against the specifications. If the property values are mapped out in the form of a diagnostic pathway, then a combination of methods, standards, and techniques can be used to optimize the process in determining whether the material is asbestos or not. To give an example, I was back out the back of Whoop Whoop at a construction site when there was all tools down because some fibrous material was found and thought to be asbestos. And I said, looks like it's time for Smyco. And one of the guys offered a cigarette. I kindly declined, but asked if I could borrow the lighter. Simply took the material, put it in the flame, it burnt to ash, and said, there we go, guys. If it were asbestos, the fibres would still be here. So I guess it's back to work. And this is where the use of simple tools to rule in or rule out material as asbestos can be done if we have a full understanding of the property values that characterises the material's identity. So in specifically looking at asbestos, we turn back to the definition and use this to characterise its identity. The property values can be unpackaged into 3 dimensions of morphology, atomic structure, and elemental composition. As a side note, when performing a critical review, it's always good to do a quick thematic analysis to find common groupings, in the same way that you might assign similar exposure groups when undertaking occupational hygiene assessments. This helps to map out and construct decision trees to optimise processes. Those who are familiar with the different analytical techniques, I want you to consider what each technique measures and what information it has in supporting these dimensions. For instance, polarised light microscopy can quickly reveal the morphology and the nature of the crystalline structure for chrysotile, amosite, and crucidolite, such that it cannot be anything but asbestos. However, in the case of amphopolite, tremolite, and actinolite, other confirmatory techniques such as electron microscopy are required. And this is specifically stated in the current Australian standard. This is because of the overlapping refractive indices of the 3 less common types of asbestos, which can be resolved through elemental composition. So now let's turn to the different techniques that may be used. Polarised light microscopy is a crystallography technique providing information on morphology and the crystalline structure. The fibres are immersed in an oil with a similar refractive index and viewed using polarised light. These viewing conditions provides evidence of the atomic arrangement, packing structure, crystalline growth, and refractive index. The refractive index being a material property that characterises the speed of light through the medium. These property values, when combined, are unique and facilitates unequivocal identification for the common white, brown, and blue asbestos varieties. The pictures below show the 4 different viewing conditions. It can be shown here that morphology can be characterised in any of these lighting conditions. The first picture shows cross-polarised light identifying the material as crystalline. The birefringence, optical orientation, and angle of extinction when combined indicates the packing structure of the material. The next photo shows the red retardation plate, which is inserted in the path of light, and that tells us which axis of the fibre has the higher refractive index. The third picture tells us whether the fibre is chromatic when viewed under plain polarised light. And finally, the colours presented under optical dispersion staining indicates the refractive index of the crystalline material relative to the oil that it's immersed in. Polarised light microscopy alone cannot unequivocally differentiate between tremolite, actinolite, and amphopolite because of the overlapping refractive indices. It's claimed by some that this issue can be resolved through assessing the extinction angle. This is wrong, as one simply needs to refer to Table 4 of the International Standard ISO 22262-1, where the HSC reference material all have parallel extinction. This is where elemental analysis is required to resolve these varieties. Other circumstances where PLM may not be able to provide unequivocal confirmation is during trace analysis, where refractive indices may not be able to be resolved because of the interferences or fibres being less than the resolution of the microscope. At 100 times magnification, this is commonly about 1 micron, where electron microscopy can easily conduct elemental analysis at magnifications of 500 to 20,000 times or more during simple routine analysis. Phase contrast microscopy is a quantitative technique used to measure the airborne concentration of respirable fibres. Because it only provides limited information on morphology and refractive index, it cannot be used to identify asbestos. It can, however, be used as an add-on test for trace analysis to rule out the presence of respirable asbestos. Caution must be applied, however, when interpreting results of respirable fibres, as they may also be created from sample preparation, as shown in the photo below, which depicts elongated mineral fragments. So I'd be wary of any reports indicating the identity of a bulk material based on the examination of countable fibres without a proper examination of the morphology. PCM has the ability to identify respirable fibres with widths of 0.2 microns at a magnification of about 400 times. This resolution is important as it is the basis of the minimum detectable fibre widths used in epidemiological studies. If lower fibre widths are examined and counted, this unravels the association of exposure with the probability of the end health effect. Consequently, if electron microscopy is used, which detects finer fibres, then the associated risk is not valid. And this is the purpose of using the HSC test slide under phase contrast microscopy, as it's a biological check on the analyst. These results may be used to assess risk, compliance with regulations relating to airborne concentrations, and the workplace exposure standards. In some circumstances, phase contrast microscopy can also assist in determining whether the refractive index of the fibre is higher or lower than the liquid that it's immersed in. And this can be helpful to select refractive index oils to reduce time in coming to a conclusion and possibly rule out the material as being asbestos if it can be shown that the refractive index is very different to that expected of asbestos. At the moment, there's more X-ray diffraction machines which are being used from the recent silica epidemic. And the instrument can also provide structural information of the crystalline lattice by measuring the distance of the spacings between the atoms within the atomic structure. The sample is bombarded with a beam of X-rays at different angles, where atoms may absorb and then re-emit the X-rays. Where there is a crystalline structure, constructive interference occurs, showing peaks at certain angles. These angles are defined by the wavelength of the X-ray and the distance between each atom along the crystalline plane. As there are a number of planes, a number of peaks arise, which may be specific to the crystalline structure. X-ray diffraction has been a popular technique in the detection of asbestos in vinyl floor tiles. An example of a spectra is provided below, showing peaks which are consistent with the presence of chrysotile at about 12.2 and 24.4 degrees 2 theta. So the correct interpretation of this result is that the presence of chrysotile cannot be ruled out, but there simply is not enough evidence at this stage to unequivocally say that the material contains asbestos. This is also because X-ray diffraction will detect non-asbestiform varieties and similar materials that may provide similar spectral peaks. Consequently, another test method may be used to optimize the diagnostic pathway based on the sensitivity and specificity of different techniques so that we can be more confident in the conclusion that is drawn. There may also be conflicting results because some commercial bulk material may include material that have similar spectral peaks to that of asbestos.
Yes, I'll have a listen to it. Cheers, mate. Thanks for that. Well done.
And maybe indeterminate. And we might also get indeterminate results which require resolution that can only be done through electron microscopy. So currently we're the only accredited laboratory for the analysis of asbestos using X-ray diffraction. And please use caution in the selection of the lab used, as the result may not be valid in context of the applicable regulation, especially if it's not used with another technique. So X-ray fluorescence, this operates by exciting electrons, ejecting them from orbits and measuring the packets of energy emitted when dropping into a lower shell. Each material has a characteristic packet of energy which can be matched with an element. The number of counts and its response factor can quantify the amount of the element present, and this technique can only provide elemental information and does not provide information on morphology. Generally, it's not used specifically for asbestos identification, but it's useful to assist with XRD analysis by defining what elements are present to supplement the spectral profile matching. Vibrational spectroscopy. I'm unaware of anyone who's using this in Australia. However, it's commonly used in Europe. This is where a beam of infrared radiation passes through the sample with a measured absorbance identifying the resonant frequencies of the molecular bonds, and it thereby provides a unique spectral fingerprint. And these spectral fingerprints can then be compared to asbestos reference material. So this also has the same limitations that are applied when interpreting the results because of the morphology. Scanning electron microscopy fires a beam of electrons across the surface with a reflected signal generated by the material's topography or composition. In the photos here, the shade of grey relates to the elemental composition, where the heavier elements appear whiter. The advantage of SEM is in providing images that support morphology when this is critical in making a decision as to its asbestiform habit, such as the photo in the bottom right-hand corner, which is showing chrysotile and its characteristic curvature. The chemical composition is determined through energy dispersive spectroscopy in a similar manner as XRF, the exception being that we can target a specific location on the fibre for elemental analysis. Transmission electron microscopy works similar to SEM. However, rather than detecting reflected electrons, it produces images via transmission through the material. The image is essentially a two-dimensional shadow providing basic morphology. And the advantage of TEM compared with SEM is it can be used at extremely high magnifications. It can detect and resolve fibrils nanometers in width. It can also provide elemental analysis through EDS, similar to SEM, and can provide structural information through analysing diffraction patterns. The disadvantage, however, is in some ability to resolve the broader crystalline habit when assessing the morphology. The resolution of the technique should also be considered when assessing morphology and the implication of respirable fibres being identified. AS 4964 implies that the identification of respirable fibres under trace analysis at 100 times magnification, but in reality, it can't. This may be partially overcome by using PCM, which identifies fibres consistent with the morphology associated with asbestos-related diseases. Where there are elevated fibre counts from airborne monitoring during asbestos removal works, electron microscopy can be used to determine whether the respirable fibres are actually asbestos or not. It could be that the respirable fibres may have been produced from the removal of ceiling insulation or carpet or some other unknown material. This additional information can put people at ease if they suspect that they have been exposed, and further analysis can quickly diffuse these sensitive situations, such as in the photo below, which shows a respirable fibre that wasn't found to be asbestos. It was just simply a calcium silicate. When analysing rocks and ores, the most common form of misclassification resides in the determination of whether the material is truly asbestiform when first analysed by other methods, such as PLM, PCM, and even TEM. In many cases, suspected asbestos may present under PLM or TEM as acicular fibres, that is, single fibres with a needle-like structure. What needs to be considered is the fibrosity of the mineral, and for it to be an asbestiform habit, you'll need to tease out the fibres which can be separated longitudinally. Asbestiform fibres are flexible and tenacious by nature, in which they should not simply break and cleave apart. We should also see that these arrangement of fibres or bundles en masse. If we turn and look at the picture on the top right, we can see that what appears to be a veiny rock, when we interrogate this and attempt to bring out and separate fibres, they simply cleave laterally and form smaller fragments. In this instance, it initially appears to be tremolite asbestos under trace analysis, in which we can also see that these respirable fibres in phase contrast microscopy. So when assessing the morphological features where the fibre is greater than 5 microns, the aspect ratio should generally be greater than 100:1. The sets of fibre bundles will generally be less than 1 micron, and there must be one or more, and preferably 3 of the following aspects: parallel fibres occurring in bundles, fibre bundles displaying splayed ends, matted masses of individual fibres, or fibres showing characteristic curvature. As we can see in the top picture, it does not conform to those specifications when we compare it to the reference asbestos below. What can be concerning is failing to place results into context. Where there are the elements that make up asbestos, there is the opportunity for asbestos to be present. What can also occur is the apparent creation of what seemingly appears to be asbestos from crushing or grinding material during sample preparation. A single acicular needle does not amount to the identity being confirmed as asbestos, and further assessment of the crystalline habit en masse needs to be considered. At what point does this become a health risk? And by what measure should material be prohibited in finding a single acicular needle? Could there be more harm than benefit in overdiagnosing some situations where there may be less than trace amounts? This is more important as we get into more sensitive analytical techniques. And here is an example of a columnar structure which has been cleaved laterally with 3 fibres presenting. All 3 fibres have different chemical compositions, with one fibre presenting as chrysotile. So should this hidden splayed end be considered asbestos? So in summarising the techniques, there is no one test which is perfect. Each has its own limitations. Ask where the uncertainties lie to unequivocally prove its identity and fill the gap. It's a matter of what information is required to be certain in the decision that needs to be made. Thank you.
Thanks, Carl. Appreciate your time today. We'll open the floor to any questions that anyone might have. I know we've got the chat room open. If anyone has any questions, feel free to put them in the chat. Or feel free to unmute yourself. it's a typical webinar where you just hear crickets. I've just got a quick question for you, Carl. So just in terms of, I guess, the methods in which would make recommendations. Obviously, when we're undertaking asbestos air monitoring and we're having high counts, typically we'll send those samples off for analysis for SEM to determine if the fibres are asbestos. Would that be, I guess, the best way forward in determining if the fibres are asbestos? Are there any other methods we should be considering when looking at high counts and confirming if they are asbestos or not? You're on mute, Carl, just before you answer.
Gives me 10 seconds of thinking time. Look, any electron microscopy is well suited for that. TEM would generally be better. SEM is more than capable of doing it as well. Probably the biggest issue is in identifying some of the fibres on, say, a membrane filter. So generally, you would want to use either a gold or silver, generally a gold backing filter, so that there's more contrast between the elements of the fibre compared to the gold backing material. But it's a good indicator to identify whether or not it's simply contamination from some other non-asbestos source compared to it actually being from asbestos, say, during an abatement project.
Fantastic, thanks for that. I think we've got a question, Fraser.
Yeah, there's one on the chat. So is there a reason why PLM is conducted in the UK on all 6 types of asbestos? And that's from Steph Warner.
Might have to ask someone from the UK.
It's one of those challenges, isn't it, where different jurisdictions and different countries are following their own methods. In terms of vinyl tile, you're talking about XRF analysis being used typically now for vinyl tile and identifying asbestos within vinyl tiles. Would that be the best method to utilise for identification of asbestos within those vinyl tiles? Obviously, the limitations with PLM.
Well, one needs to be cautious about simply just using XRD. It doesn't provide the morphology, and as I explained as well, that you might get some material which has similar spectral peaks as well, and also the detection limits. So it may be a good screening test, and we particularly use it as a tool in determining what might be the next best test method, whether it may be PLM or electron microscopy.
Fantastic. Thanks for that, Carl. Any other questions online, Fraser? No, I think
No more questions at the minute, no.
Sure, there'll be some more questions at the end. Thanks for that, Carl. Appreciate your time today. I'd now like to introduce Laurent. Let me just share my screen quickly. Okay. I'd like to introduce Laurent Fenouil from COHLABS TEM. Laurent is a business development manager with over 8 years of experience working in multi-sector industries and multi-sized companies in France, the USA, China, and Australia. Laurent specialises in electronic engineering and innovation management and was responsible for developing biotech and COPD devices and digital OHS solutions for startups and bigger organisations. Laurent came to Australia in 2019 as part of AHCA Group, a French occupational hygiene company, and has participated in the creation and development of the joint venture COHLABS TEM, along with local and international experts to bring awareness and skills around TEM technology applied to asbestos analysis. Laurent will provide a basic introduction of optical and electron microscope technologies prior to an overview of the 3 analytical criteria used in TEM analysis for unequivocal asbestos determination through detection, classification, and identification. Laurent will provide information on how TEM analysis can be used for analysis of membrane filters following the NOSH PCM analysis. He will also provide examples of some results for a range of bulk and airborne samples analysed via TEM. Welcome, Laurent.
So thank you very much, Carl. Thanks, John, and thank the AHCA for giving us this opportunity today to share some insights about different techniques around asbestos analysis. I'm gonna concentrate this presentation on transmission electron microscopy in asbestos identification and quantitative analysis. So a bit of introduction first. COHLABS TM is an early 2020 international skills partnership between 3 companies, one in Brisbane, a laboratory called COHLABS, an equipment provider called PPS, and a French laboratory called AHCA, specialized in TM analysis. About the agenda, I'm gonna go through a TM overview first, and then I'm gonna present the analytical criteria that we're using to identify and quantify asbestos. I'm gonna speak about the processes and standards, and I'm gonna show some case studies that we've done. About the TM itself, if you've never seen what it looks like, it's kind of a big microscope, about approximately 2 meter high, and probably the same in width. The main difference that you can spot sometimes on those kind of microscope is one has a direct reading screen. So for example, the one on the left, and other TM has direct camera integrated into the microscope, and that's the case of the one we're using at COHLABS as well. So if we look at the differences between those kind of those different technology, as you can see, the conception is quite similar between light and electron microscopy. The main difference is obviously the source. On one side we have a light source, and on the other side it's an electron source. The electron source is generated in applying high voltage on a tungsten filament, and that generates an electron beam. And in the case of a scanning electron microscopy, this beam is controlled using a scanning coil, and this beam is, as its name said, scanning the sample directly, and that gives this kind of 3D representation of what you're looking at. The difference with transmission electron microscopy is that the electrons transmit the sample, and we don't have a 3D representation of the sample, but we have access to the crystalline structure and other characteristics. So the image is a bit different using an electron microscopy, I mean a transmission electron microscopy. So here are some examples. You have chrysotile. You have an example of the cell, or to get in the context, we have an example with the coronavirus. And sometimes we also are facing some funny shapes. So now I'm going to move on the analytical criteria. The first criterion is the morphology. So you might know that asbestos fibers are divided in 3 different groups. The first one is the World Health Organization groups, with the characterization of the fibers that everyone knows. We then have the thin asbestos fibers and the short asbestos fibers. These 2 last groups, the fibers are too small to be detected by either classic techniques like PLM and PCM. So to reach those fibers, you need to change the technology and to switch from light microscopy to electron microscopy. So as you can see in the comparison in the table between all those different microscopes, the resolution and the minimum object size detection is quite improved using electron microscopy, and especially transmission electron microscopy. So in terms of analysis, TEM is able to analyze bulk and airborne samples, and for both, it's able to detect those three different groups of asbestos fibers. I just put a note for the airborne analysis because even though we are able to detect thin and short asbestos fibers, we cannot compare the results we have with the Australian regulatory standards because those two category of fibers are not taken into consideration in the standards yet. Now, if we talk about the second criterion we are using is the chemical composition given by EDS, energy dispersion X-ray spectrometry. And thanks to this, we can have a look at the signature of the fiber we are looking at, and we can compare it to the signature we have as the references for every types of asbestos that we have. So the 6 types, either if it is commercial or non-commercial. And the third criteria is the diffraction mode. And this is basically in concentrating the beam on the fiber we are observing, and that gives us the access to the atomic arrangement and or the crystal structure of the fiber itself to know if it's an isotropic or an isotropic fiber. So if we need to place all of this in a graph, so if we are interested only in morphology, it's SEM and PCM are the techniques that can be used for morphology only. If you want to combine this with the crystalline structure, you can use PLM and TEM, as I just explained with the electron diffraction. It's also possible to do an XRD to get access to the crystalline structure and to deduce the chemical composition as well. Or an EDS can be used straight away, as I've just presented before, to get the chemical composition of the fiber we are observing. So if we only refer to the morphology given by the characterization of the 3 groups of fibers, morphology generally gather all fibers which meets this morphology criteria. Then for the crystalline structure, as I said before, it's knowing between which one is isotropic or anisotropic material. We know that for asbestos, we are going to look for an anisotropic material. And the chemical composition gives you the composition of all the fibers you are looking at, either if it is asbestos or non-asbestos. So electron microscopy are most of the time paired with an EDS. In the case of a SEM, you are in the side where you are looking at the morphology and the chemical composition. So you can look at fibers of asbestos, but also you can have a look at asbestiforms and fibers similar in composition to asbestos. So in this case, you can you can check out the characterization for belts and air filters within the SEM range resolution. Just some notes for the bulks. So if you want to get the third criteria with bulk, you have to proceed with a complementary analysis that can be done either by PLN XRD or TEM to get the crystalline structure. and to get an unequivocal identification. This crystalline structure analyze is not possible using air filters, using XRD, because the filter is not loaded enough for an XRD analysis. And then the couple TEM and EDS is used for, it gives access to all three criteria, and that's helping us to have an unequivocal identification of the 6 out of 6 types of asbestos for bulks and air filters. So this is an example to show the importance of the third criteria, because if we are looking only at the morphology and the chemical composition between those two pictures, you would think that these two fibers are similar. And if you compare the chemical composition to your references, you might think that these two fibers are indeed anthophyllites. But to have an unequivocal identification, you need to look at the crystalline structure, and that's where you can get surprised sometimes. So for this same example, as you can see, the fiber on the left has hexagons pattern for its crystalline structure, while on the right you have parallel rows, and that's typically what we are expecting from an asbestos fibers, is to have those parallel rows. So thanks to this third criteria, you can unequivocally identify anthophylite on the right, compared to fiber of talc on the left. Now I'm going to go through the process and standards we're using. In terms of bulks, we are using the process ISO 22262, and for the filters, we're using the NIOSH 7402, which is an American standard. So talking about the bulks, either if it's non-fibrous or fibrous material, we are going to first have these samples analyzed by PLM. That will give us 3 potential outcomes. Either it is positive, either it is non-asbestos detected, or unknown mineral fibers. For those 2 last cases, we are preparing then the sample using the international standard ISO 22262, and then we're going to proceed to a TEM and EDS analysis to have a negative or a positive confirmation with an unequivocal identification of which asbestos we are looking at. For filters, we are using PCM first. 2 reasons for that. One main reason for that is that we need to have PCM counts if we find some fibers using PCM. And if no fibers are detected, we're going to ask for confirmation. So for either outcomes, we are preparing then the sample using the NIOSH 7402, and we're going to go through a TEM and EDS analysis as well for quantitation this time, and unequivocal identification as well. So why we're using the NIOSH 7402? So the 7402 is an American standard for air samples. It's done in complement of a PCM analysis, and it's a direct method. So it uses the same filter as the one for the PCM analysis. And the 7402 is basically calculating a ratio between the number of asbestos fibers on the number of visible fibers. So thanks to this ratio, we get the percentage that we get can be directly applicable to existing PCM counts and the Australian occupational exposure standards. That's why we need to get the sample analyzed by PCM first. It's to get the counts. And how do we determine the concentration in asbestos? It's basically in applying this TEM ratio on the by the PCM counts, and we got the concentration of asbestos fibers per milliliter. Now I'm going to go through some case studies. So an example of bulk analysis. This one was a false negative given by PLM. It's a vinyl tile. So as you can see, under the stereo microscope, we can't see any fibers. But once we analyze this sample through with the TEM, we found what we call a carpet of chrysotile fibers. Mostly of them were in thin and short asbestos fibers, so definitely too small to to get detected by light microscopy. Another example of false negative for bulks, still vinyl tile. Same results here. No asbestos was detected using PLM, but we found trace of tremolite in the first category of fiber, the HU fibers. For this one, under the PLM, we found unidentified mineral fibers, and that's mainly because those three picture here represents the three non-commercial asbestos fibers. So with the TM, we were able to differentiate between which one was actinolite, anthophyllite, and tremolite fibers. Another example of false negative for bulks, this one in a different sample, we were analyzing crayons, and the PLM didn't find any asbestos, while we found trace of tremolite using TEM analysis. An example of natural occurring asbestos. So this sample was marble-like benchtop from a greenwork material. And as you can see, there's different fibers here. So on one side, we found tremolite, asbestos fibers, and on the other side, we found another material, which is not asbestos. It's called lysotite. Both material were under the WHO characterization for fibers. So we were able to differentiate between which one was indeed asbestos and which one was not asbestos. An interesting example of air filter. So this filter was analyzed by using the NIOSH method. And as you can see on the picture, sorry, you can find three different fibers. So two amosite fiber and one chrysotile fiber. And as you can see, they are all not part of the WHO characterization. So it's short and thin asbestos fibers mainly. And for this example, if we had to give the results, we would say that we didn't find any fibers because they were not part of the WHO characterization, and so they cannot be integrated to compare with the Australian occupational exposure standard. And I think this is one of the main difference between other countries that are using TEM, for example, the US or France. We had toxic, I'm giving you the example for France. We had this toxicological studies about thin and short asbestos fibers. And it appears that these toxicological studies found that thin asbestos and short asbestos fibers are also carcinogenic, especially the thin asbestos fibers. And that's why to be able to detect and to count those fibers, the regulation requires now now since since the 90s, the use of TEM to be able to count those fibers. So TEM is the standards in those countries because we know that those fibers are carcinogenic as well. And that's the main difference with the Australian standards. So then there's another example of filter. So this one was analyzed by PCM, and this fiber were counted. But when we analyzed this using TEM, we found that it was not an asbestos fiber, but it was an refractory ceramic fibers. In terms of what we integrate in the report, so that is basically the 3 criteria that we use to justify the fiber we've just analyzed. We compare them. So on the top, you have the analysis, and on the bottom, you have the references that we have. So those references have been done during the calibration of this specific TEM. So we are sure that when we are looking at this morphology or this chemical composition or this electron diffraction, we are sure to identify the right fibers and the right asbestos type. So in conclusion, TM gives access to those 3 criteria I've just mentioned. So the chemical composition given by EDS, the crystalline structure given by the electron diffraction, and the morphology thanks to the high resolution of this microscope down to 0.1 nanometers. Those 3 criteria gives an unequivocal identification of the fiber observed in one go and out of all 6 types of asbestos. And the results we have can directly be applicable to the Australian standards for bulk and air samples. Now, if you're asking yourself where we are now in terms of accreditation, so this project of TEM has 3 years now. We started in 2019. We built the company in 2020, as I mentioned before. We brought experience from France and the US to assist for that. And we applied for the accreditation in November 2020. We finally had this audit 7 months later in June. The audit was separate in 4 weeks, so it was a 4 weeks long audit, and we did it remotely with the US. And thanks to Frank Ehrenfeld that assisted NATA in auditing the TEM on the technical aspects. And we are now pending NATA approval for the accreditation. So might be very soon. It's just a question of a couple of weeks or months. And I think this is it for me. So thank you very much. And if you have any question, I'll be happy to answer.
So my question's really to Carl and Laurent. At what percentage detection are you getting down to for XRD for floor tiles, and then the same to Laurent for TEM? At what percentages are you accurately identifying asbestos in the source material?
We might start with Laurent and then over to Carl.
Yes, I'm not quite sure. I think it was 0.01%. I mean, it can be down to 0.01%, much lower.
Okay, and Carl, same question for you.
Yeah, it's probably, in the way that we use it, it's probably more a matter of misclassification in terms of looking at a receiver operator curve in terms of a false negative, false positive when compared against the reference material, against a reference standard test. So this is where sometimes you need to look at not so much how much is in there, but what evidence is there in it meeting the specifications. So we're looking at that spectral peaks and comparing that to whether it may be identified or suspected of those crystalline materials being there, and then comparing that to, say, PLM. So we don't use it directly by itself. It needs to be used with another technique. So it's more looking at confidence intervals rather than a detection limit in itself.
Fantastic, thanks, Carl. Did that answer your question, Richard?
Absolutely, yes.
Okay. Any other questions? Please feel free to raise your hand and ask away.
There's one from Sam O'Callaghan, sorry. For both presenters, how much does it cost for bulk sample and air sample analysis using the various methods discussed?
Laurent, we'll start with you.
Well, I would say it depends on the type of sample we have. So I'll just suggest, who was asking the question?
Samantha O'Callaghan.
Yeah, so I think you got my contact, so you can send me an email for which type of sample you're thinking about, and maybe we can have a chat.
No worries. And Carl?
The same applies. It depends on the complexity of the material. So, to be honest, sometimes you can just spend a whole day on one sample. So it really depends on the type of sample.
Both spoken like true consultants, never committing. We've got a question here around turnaround times. How quickly from, I guess, receipt to delivery of results would the samples take to analyse? Laurent, start with you.
Yeah, so generally we are going through a 24-48 hours.
That includes preparation, analysis and reporting?
Yeah.
And Carl?
Depends how much sleep I want that night, really. I mean, it's really a matter of sample preparation. What other techniques? I mean, look, generally it's not just one technique that you might apply. You know, you might start off with your PLM and other things as well. It just really depends on, again, the complexity, sample preparation. But look, stuff can get turned around if need be, you know, within half a day. But, again, it just depends on the complexity and sample prep.
Oh, fantastic. Any more questions from anyone? No? I'd like to thank everyone for attending today, and a special thanks to Laurent and Carl for presenting today. This presentation will be up on our website in due course once we're able to process it and get it on there. So you'll be able to access it there. As a closing remark, if any of our members are keen to present on any new innovations coming into the market or interesting case studies that they may have that they'd like to share with their peers, we'd encourage that, and would ask you just to reach out to one of the executive committee and put your hand up to be part of that. We're hoping, I guess, with the COVID situation the way it is at the moment, we'd be looking at running webinars probably every 2 months. So if anyone has anything that they'd like to present to the group, feel free to put your hands up as well. So thank you everyone for attending today, and thank you Laurent and Carl, and enjoy the rest of your afternoon. Thanks everyone.
Thank you very much.